Hi everyone. Let us now continue our discussion on gases. But for lecture 4, we will be dealing about real gases. The ideal gas law describes correctly the behavior of most gases over a limited range of pressure and temperature. So we know that ideal gas equation, PV is equal to nRT, is a limiting equation which holds true only at certain conditions. But on this topic, you will realize that real gases show deviations from perfect gas law because molecules interact with one another. After studying this module, you should be able to accomplish the following outcomes. So one is differentiate the behavior of ideal and real gases and express the limitation of the ideal gas equation. Secondly, define the compressibility factor and explain the effect of temperature and pressure on this factor. Next is to write and explain the basis of van der Waals equation of state for real gases. Fourth is to represent graphically and interpret the isotherms of a real gases at different temperatures and describe the critical state of a gas and define critical temperature, critical volume, and critical pressure. Now, if we will differentiate ideal and real gases, so in terms of the equation, ideal gas equation, ideal gas always follows the limiting equation. But for real gases, this is only applicable at very low pressure and high temperature. In terms of molecular volume, we are considering gases as point particles. So 0 for ideal gases. So for ideal gases, but for real gases, it's small but non-zero. In terms of molecular attractions, 0, we are not considering the intermolecular forces of attraction in ideal gases as compared with real gases. And molecular repulsions is also 0 for ideal gases, and we are considering molecular repulsions for real gases. So a point to keep in mind is that repulsive forces between molecules assist expansion of gases. So if there's repulsive force, so there is gas expansion. And attractive forces assist compression of gases. Now, in terms of molecular level, if we will be considering perfect gases, so the ideal gas conditions is low pressure and high temperature. If you will see it in a molecular level, gas molecules are very small. So they exert forces on the walls of the container, but not on each other. So the particle size is very small compared to spaces in between them. And the interactions between particles are not significant. For real gases, so we are considering high pressure here and low temperature. So gas molecules have volume, which reduces the volume in which they can move. They exert attractive forces on each other, which reduces the pressure, and they exert forces on the container walls. So in terms of particle size, this is more significant compared to space between particles. And we are now considering the interactions between particles. Now, if we will take a look on the isotherm of perfect gas. So example, if you will plot P or pressure versus volume. So example, this is PV at T1. So this is your first isotherm. PV at T2 and PV at T3. So this is increasing temperature. So take note that if the temperature is lower, the isotherm is getting closer to the axis. But we are keeping here the hyperbolic change since PV is equal to constant. So you will realize that for perfect gases, the isotherms are perfect and they almost look the same. However, for real gases, so example, we have T1 here and we have T sub 2 here. So this is at high temperature, it's nearly hyperbolic or nearly ideal gas. But you will see the deviations as the temperature becomes lower. So we now have what we call the distorted hyperbolic function. Uh, this is comparing with ideal gas. They are not perfect isotherm. Now, you will realize that this is because of a phase change, like in terms of liquefaction or condensation, that is happening due to intermolecular forces of attraction. Now, considering the molecular interactions, so let's say first we have a HBr molecule, or which is a polar molecule. So we have a dipole-dipole interactions between the partially positive and partially negative. Now, if the distance is very large and low pressure and high temperature, so there's no point of interaction. So going back on this slide, so if the distance is very high, low pressure and high temperature, so there's no interaction between the two. But if you make the distance closer at moderate pressure and low temperature, attractive forces is possible. So because there's small enough space for attractive interaction. However, if you make the molecules very close or the distance is too close between them, what is happening here is the repulsive interaction at high pressure and low temperature. So as expected, the molecules, they will repel with each other. Now, to summarize the molecular interactions, so if we have a moderate pressure, low temperature, and there's a moderate distance between the two molecules, attractive forces are dominant. So what is happening? It pushes the molecules closer together. And the molar volume of real gas is less than the molar volume of ideal gas. What is also considered here is whenever there's attractive force, gas is more compressible. Now, for repulsive forces, so if the distances between the two molecules are too close, so there's a high pressure and low temperature, it pushes the molecules farther together or they repel with each other. And then in terms of molar volume, molar volume of real gas is greater than molar volume of ideal gas. So in terms of the property of gas, if there is repulsive force, gas is less compressible. As I mentioned earlier, repulsive forces assist expansion of gases. So this is significant when molecules are close to one another. They are operating at high pressure, wherein the intermolecular distances are nearly a single molecular diameter. And attractive forces assist compression of gases. And they can have influence over a long distance and operative at moderate pressures. Now, the extent of deviation of a real gas from ideal behavior can be shown through the ratio of the molar volume observed between real gas compared with ideal gas under the same conditions of pressure and temperature. Now, this is known as the compression factor. So, Z, or the compression factor, refers to the ratio of a real gas over ideal gas at the same condition. Now, what can we say about the compression factor? If Z is equal to 1 or close to 1, so we have an ideal gas. So, if the gas is less than 1, what is happening here? Attractive forces are dominant. The volume of a real gas is less than molar volume of ideal gas. And gases are more compressible because the molar volume is less than ideal gas. So, however, if you have Z greater than 1, so number 1, repulsive force is dominant. the molar volume of a real gas is greater than the ideal gas under similar conditions, and the gas is less or becomes less compressible. So keep in mind that compression factor is also dependent on pressure. Now let us take a look at isotherm, or variation of Z with pressure of a certain gas at varying temperature. So recall that compression factor of a gas can be defined as Z is equal to PVM over RT. So this equation was derived from molar volume equal to RT over P. And Z is equal to molar volume of a real gas over ideal gas. So our equation becomes, for compression factor, is Z is equal to PVM over RT, wherein molar volume, Vm is molar volume. Now, if C is equal to 1, so we have an ideal gas. If C is less than 1, compression is favored due to dominance of attractive forces. And if Z is greater than 1, expansion is favored as repulsive forces come into play. Now, let us take a look at variation of Z with P of a certain gas at varying temperature. So let's say if we will plot Z versus P. Now, what is happening here is if we have a perfect gas. So perfect gas, this is a straight. Z is equal to 1 all throughout. Now, if we have a high temperature, what do you notice? So at high temperature, kinetic energy is always higher because temperature is directly proportional with kinetic energy. So Z is deviates from 1, so it's always higher than 1. And then, if you will take a look on this point, or this area, if pressure is approaching 0, what is happening with the molar volume? Molar volume is also approaching infinity. And if P is equal to 0, Z is approaching 1. So this means that there's no intermolecular forces of attraction. But at lower temperature, up to this point, so lower temperature, so what is happening here is the lower the temperature, the lower the kinetic energy. So at this point, phase change is happening, like condensation. So what happens to the molar volume of a real gas? Molar volume of real gas is much greater than ideal gas, because in condensation, it is changing from gas to liquid. So you know that the molar volume of liquid is much, much less compared with volume of a gas. So now, in this figure, or yeah, we have what we call boil temperature. So what is boil temperature? Boil temperature is a temperature at which gas follows the ideal gas law. It follows the ideal gas law at an appreciable pressure range, because at a higher temperature, what do you notice? Z is greater than 1. Compression factor is greater than 1. Gas is less compressible, and repulsive forces dominate. So for this lower temperature, Z is always less than 1, and attractive forces dominate. So at this point, this is where deviation is happening. So from ideal to real gas. So as I mentioned, Z is also dependent on temperature. So at a certain temperature, like boil temperature, Z is equal to 1 over a range of pressure. So below, take note, below boil temperature, so below boil temperature, Z is decreasing as pressure increases. At a certain pressure, Z reaches a minimum value. So this is at this point where Z reaches a minimum value, after which its value increases with increasing P. This is happening at this point. Now, comparing with above boil temperature, Z is always greater than 1 as pressure is increases. Unlike lower temperature, lower than boil, it is decreasing and then it reaches a minimum point and then Z increases as P increases. Now, for variation of Z of different gases with pressure, so take note at a very low pressure, um, P approaching 0, the molar volume is approaching infinity, and Z is equal to 1. So this means this is an ideal gas. So at high pressure, very high pressure, molar volumes are greater than ideal gas, Z is greater than 1, and repulsive forces are dominant. At low to moderate P, or pressure, attractive forces are dominant, and molar volume is less compared with perfect gas. So at this figure, so example, this is the perfect gas. So you could see that um, in hydrogen, Z is always greater than 1. So repulsive forces are dominant. So the graph of hydrogen, Z is always increasing as pressure is being increased. However, in the case of ammonia, NH3, C2H4, CH4, it's decreasing. So it has something to do with the intermolecular forces of attraction. So comparing with CH4 with C2H4. So this is more hydrogen compared, no, greater molecule compared with CH4. And in NH3, hydrogen bonding is strong. You have a greater dip and strong intermolecular forces of attraction compared with H2 as repulsive forces being dominate. So you could see that compression factor is dependent on pressure and temperature. And you will realize that it has something to do with the property of molecule and as intermolecular forces of attraction are present. Now, let us solve one problem on compression factor. The mean molar volume of air at 60 bar and 400 Kelvin is 0.9474 cubic decimeter per mole. Are attractions or repulsions dominant? So we will solve Z here. Z is equal to, so kindly disregard this, PVM over RT. So PVM over RT. So 60 bar, convert this to atmosphere, 0.987 per 1 bar. Now the molar volume is 0.9474 divided by R. So in this case, we will be using 0.08205 liter atmosphere per mole Kelvin, temperature in Kelvin. So bar cancels out atmosphere as well as liter, mole, and Kelvin. So Z is unitless. So we will be getting 1.709 and repulsive forces are dominant. The behavior of real gases can also be expressed by means of what we call virial equation of state. So what is virial equation of state? So they are determined experimentally by curve fitting. So experimental deviations of C from the ideal can be used to construct an equation of state. So later on, we will be discussing Camerling-Onnes equation of state, and then the Beatty-Bridgman equation of state. Virial equation of state involves a power series and is derived from statistical mechanics and obeyed by real gases are not at very high pressure. So virial coefficients for a real gas with large molar volumes and higher temperatures, the isotherms are almost identical to those of an ideal gas. However, there are some differences or small differences which suggest that perfect gas law is only the first term in the power series. Now, we have a general form here. In terms of pressure, PBM is equal to RT, 1 plus B prime plus C prime P squared, and so on. In terms of molar volume, we will be using RT, 1 plus B over Vm plus C over V squared M. So these are called B and B prime, C prime, B and C are called virial coefficients. So they vary with temperature and gas type, but prime, B prime and C prime will be using if we have pressure, and capital B and C if we have in terms of molar volume. Now take note, the coefficients B and C have to be evaluated at each temperature. So let's say there's a specific temperature value, there's a specific B and C or virial coefficients value. If pressure is equal to 0, this is close to ideal gas law, but not really exact. If P increases, B contributes linear relation between Z and P. And if P is higher, C and higher order terms contribute, which deviates from linearity. Now, the deviations of real gases from ideal behavior can be attributed to, number one, the volume occupied by the molecules of real gases, and number two, the attraction between the molecules of real gases. Now, example, in the case of methane, so these are the virial coefficients at a specific temperature in degrees Celsius. Take note of the values. So let's say B prime, it's times 10 to the negative 3 per bar, and so on. Now, here are the coefficients of B, C, and D plotted as functions of temperature. So they were, as I mentioned, they were determined experimentally. Now, second virial coefficients for different gases, argon, carbon dioxide, N2 or nitrogen gas, xenon at specific temperature are also given, and more values are given in the data section. I also included the values in the resource section of our course site. Now, to summarize the virial equation of state, as P approaches 0, the virial equation Z is equal to 1 plus B prime P plus C prime P squared. So if we will take the common factor, PBM is equal to RT, and this is the equivalent of Z. So as P is approaching 0, the gas behaves ideally. So this would be cancelled out. But in terms of molar volume, as molar volume is approaching infinity, the virial coefficient terms are also cancelled out. So thus, if the gas behaves ideally, we will be using PB is equal to nRT, or PBM is equal to RT. Now, take note that third virial coefficient C, or C prime, is usually less important than the second coefficient. So, values of the virial coefficients of a gas are determined from measurements of its compression factor. Now, let us try to solve one problem on virial equation of state. What pressure would 4.56 gram of nitrogen gas in a vessel of volume 2.25 cubic decimeter exert at 273 Kelvin if it obeyed the virial equation of state? So for nitrogen, B is equal to negative 10.5. Take note of the unit, it's cubic centimeter per mole. So we will be using P is equal to RT over Vm multiplied by 1 plus B over Vm. Bm is molar volume. So 2.25 cubic decimeter per mole, 0.163. So we will be getting 13.8 cubic decimeter per mole. So substituting in the equation, virial equation of state to solve for pressure, R multiplied by T over Vm multiplied by 1. This is negative because the value of capital B is negative 10.5, and we convert this to cubic meter per mole. 1 minus 1.05 to the negative 5 all over 0.0138. So the pressure is 1.64 times 10 raised to 5 Pascal or 164 kilopascal. So in the second part of the lecture for real gases, so we will be discussing the other equations of state, like the van der Waal equation.
Kill that bitch.